Hello, I am Raphanel, and together with my colleague Creignou, we are going to present our project entitled Directional Dependence of NDVI for Forest Canopies. To begin with, the NDVI is a commonly used index to assess vegetation density and health from satellite or aerial imagery. It's calculated using the red and near-infrared bands of the electromagnetic spectrum. For this project, we use the software DART, Discrete Anisotropic Radiative Transfer. DART is a three-dimensional radiative transfer model developed since 1992 by CESBio, a joint research unit affiliated with the CNRS. This software makes it possible to simulate remote sensing image and model the radiative balance of landscape, taking into account a complex interaction between the Earth's surface and the atmosphere. Here is our field, and here are our trees. For this study, we use DART to simulate NDVI under different illumination and observation conditions. First, we place the sun, which will illuminate the entire field, and then we place the satellite, which will observe it. This setup allows us to measure the NDVI under different conditions. More specifically, we vary the sun's angle to 30 degrees, then 16 degrees, and then repeat the process by varying the satellite angle to the same values. This results in 9 experiments in total, as shown in the table. This setup allows us to generate a diverse set of experiments, which in turn enable us to compare the results obtained. We begin our analysis with the case where both the sun and the observer are located at the zenith.
In order to input the position of both the sun and the camera, most of the work will be done in the single direction section and the perspective camera section. The process to input the position of the sun is quite simple and direct, as you just have to write down the value of the zenithal angle of the sun. But for the camera's position and orientation, you have to work out the conversion between spherical and Cartesian referential using trigonometry. For the location of the camera, the y value is always set to 0, and we fix the z value to 15. Therefore, we can deduce the value of x, knowing the value of theta, the zenithal angle. And for the camera orientation, the set of equation is a bit more complex and displayed on the screen. Starting from the most basic position, which is both sun and camera at the zenith position. On this image, we can see some green spots, which correspond to the less vegetated area of the field, which makes sense because there is holes between each trees that are less vegetated. We can also observe an already high value of NDVI on the rest of the field. Now this image is the result we get from the situation where the camera is now placed at a zenithal angle of 30 degrees. You can see on the right of the screen that the value of the position and direction of the camera have changed. This set of value is obtained using the formula we explained before. Overall, the description of this image is quite similar to the description of the previous one, and the same thing can be said from the third image you see on the screen right now. Now let's look at the images we get when we place the sun at a zenithal angle of 30 degrees. On this image, the first thing that catch our attention is that the green spot that we were seeing on the first set of images at sun at 0 degrees are no longer visible here. And as we change the configuration, you can see that the image remains quite the same, but overall we can say that the general NDVI value has increased for the zenithal angle of the sun, going from 0 to 30 degrees. And finally, the 3 configuration where the sun is placed at a zenithal angle of 60 degrees. On those 3 images the presence of the large white stripe is due to the extreme placement of the sun. This luckily does not affect the quality of the result in a physical way. And again, we can observe that the general NDVI value has increased compared to the previous ones. As I already mentioned a few times in the observations, there is a global tendency of the NDVI value to increase when the zenithal angle of the sun increases. And because the configurations where the zenithal angle of the sun is set to 0 are the only one to show the green spots, therefore they are the closest to the reality, which means that in reality it is better, in the sense of more correct, to make measurements in the middle of the day where the sun is the closest to the zenith, and you particularly want to avoid the situation where the sun is close to the horizon, which are the beginning of the day and the end of the afternoon.
In this video, we saw the importance of the solar zenith angle on NDVI values, as well as the relatively low influence of the satellite's angle. We could have broadened the scope of our study by introducing additional constraints such as terrain relief, clouds, or atmospheric effects. This opens up new questions regarding NDVI. For example, how to NDVI vary with shadow or atmospheric condition, or does the NDVI change if the satellite observed from an angle opposite to that of the sun? This question will surely be answered in other projects. Thank you for listening.